Good morning, everybody. Good afternoon, good evening, wherever you are.
Hello.
We have a super special session in that.
Encore.
Yeah, we're holding it early. We're holding it early in Europe anyway. But hopefully, we've got a Node 2020 extended session that is nice and time friendly if you are based in the Pacific region. So if you're in New Zealand, if you are in Australia, if you are in Japan and other parts of Asia, hopefully you're going, yes, this is a sensible time for us to watch this live.
Post it in the chat where you're from. Let us know where you're from, where you're watching this.
Drop in the if you're watching us, drop in the chat where you are. We'd love to know. So we have got, this is our penultimate Node 2020 extended session. We've got two fantastic talks lined up for you. So we're going to dive into those shortly. And what we would say here, so we're going to have some questions coming in. So if you've got questions, drop them in the chat. At the end of both the sessions, we're going to go to a panel discussion where we're going to read out your questions, so drop them in. We're keeping an eye on that. And yeah, enjoy the show. So what we're going to do, we are going to hand over to Monojit Basu. So he's going to give a quick introduction to himself, his company, and his talk. So Monojit, over to you.
Hi, thank you. Thanks everyone for joining, especially for those who are joining so late. Thanks for the opportunity to talk at Nodes 2020 extended session. The topic for my session is manifolds in semi-supervised learning. So this is about machine learning, and I am Monojit. I am the director of a company called Teijeiro in Bangalore, India. We work on cloud computing analytics, machine learning, IoT, and we are a consulting company. So a little bit of background about myself. I have worked earlier at IBM, Sun Systems, and various other companies, product development, and then I started off this company on my own. So without further ado, I just want to give a quick background about what this session is about, and then with a little bit of context setting towards the earlier part of the presentation, and then more into the details about the machine learning aspects that I want to talk about. So firstly, we will talk a little bit about semi-supervised learning and graph-based algorithms for semi-supervised learning. Semi-supervised learning is something that is a little more recent compared to a lot of other stuff that we see, including the scikit-learn kind of algorithms that we have in Python, the R package, as well as the neural networks. Although neural networks, deep learning is coming up big time now, the theoretical underpinnings was available long time back. Compared to that, semi-supervised learning is a little bit of a recent phenomenon, and graph-based algorithms are very effective. So hopefully the Neo4j community will be interested in some of these things. So we will talk about, we'll introduce semi-supervised learning, and then we will move into what is a manifold exactly. It is related to graphs, otherwise obviously it doesn't fit into this kind of a session. It is about graphs, but a little more involved in terms of the mathematical background, mathematical theories around it. So we will go into that a little bit of the mathematics and algorithms part of it. And then we will go into some classification algorithms which use, basically exploit the manifold structure in order to get the classification right. And then finally, we will talk a little bit about how we can implement it in Python, because that is one of the common languages that people use for machine learning. And then we'll close out the discussion with some final thoughts. So let's start with semi-supervised learning first. So typically when we do classification, let's say we are trying to detect whether a transaction is a proper, a valid transaction or a fraudulent transaction. Most often we depend on data that is fully labeled. So the training data, the data on which the model is trained, we have all the data items with certain attributes. For example, the time when that particular transaction was done, the place from where it was done, the amount involved, and things like that. And then we also have a label where we call this, we know of whether the transaction is fraudulent or valid. So this is the training data from which we train the model, and then we can probably apply it to new data, novel data, which we don't know, which can come in the future also. Semi-supervised learning is a little different because it takes advantage of both labeled as well as unlabeled data. Thinking about it, there's lots of domains where there's a lot more unlabeled data than you have labeled data. Text, for example, think of all the news items. If you're going to tag them, it's not humanly possible to tag all the text pages, the text items, the web pages that we see on the world. People try to do crowdsourcing nowadays, but even with that, sometimes it is not feasible because there's a data privacy issue in some cases, for example, in healthcare. But what happens is, if you leave out that data, you may actually leave out some information about the distribution of that data, which will not give you the kind of robust model that you're looking about. So very briefly, what semi-supervised learning can do is actually take advantage of both labeled as well as the unlabeled data. In a classification problem, typically what we're trying to find is the probability of the label given the data. Now, how the unlabeled data helps is that it provides us a better approximation of the probability of X, where X is the data. And you use the labeled data for probability of Y given the data. So you can use both the probability of Y given X as well as the probability of X itself, whereas the probability of X improves by using some of the unlabeled data. So that is how semi-supervised learning is becoming more popular, more hotly researched these days. In order for this to work, there is a certain property that should hold, and that property is called a smoothness property. What it means is, very simply, if there are two data points, two x's, x1 and x2, that are close, then their labels y1 and y2 should logically be similar also. So this is an assumption based on which semi-supervised learning works. Now, there are lots and lots of algorithms in semi-supervised learning. To start with, I'll give you a very simplistic algorithm, which is called self-training. All it means is, so we have the labeled data and we have the unlabeled data. So let's say 20% of the data we have is labeled and 80% is unlabeled. So what we do is we gradually grow the labeled data by taking small parts of the unlabeled data, maybe say 10, maybe 2% or 3% of the unlabeled data at a time, and find those examples which can be labeled most confidently by a baseline algorithm. Let's say it could be logistic regression. It could be a basic k-means nearest neighbor regression, something like that. And we gradually grow the labeled data set in such a way that the more confident labels are pulled in, and the label set increases over time. Now, this is a baseline algorithm. It is too simplistic. It doesn't work always. The relevance for Neo4j community is that there is a lot more algorithms based on graphs actually, and there are actually a lot of research around graph-based algorithms where the distances between nodes of the graph, the connectivity between parts of the graph, all those kinds of aspects can be really utilized to come up with a lot more robust algorithms. And we will come with some examples. For example, just to pick up one, say min cut. Say if you can create a graph of all the data, then it could be possible to separate the different labels into two or more connected components. So that automatically leads us to algorithm for classification. Then there are many other algorithms like algorithms based on graph kernels, etc., etc. We will talk a little bit about the label propagation algorithm, which is some kind of the first algorithm, graph-based algorithm that we typically come across when we talk about semi-supervised learning. What it means is that let's look at the figure in the at the middle of the page. So logically, we would expect that if there are two labels 0 and 1, logically the zeros and ones should be two at the two edges, the two distant edges of the graph. Logically, that's because they should be distant from each other. Think of the smoothness property. And then we have a lot of unlabeled data in between. The unlabeled data are those with the dotted spheres. Now, what happens is this algorithm finds a probability of one node jumping into another by creating a transition matrix. The way it does is it starts with the weights. It starts with a graph and weights between the edges of the nodes of the graph. How are these weights created? These weights are created in such a way that the more similar the two vertices are, the larger will be the weight between them. So this can be easily manipulated, and we can create a graph like that. From those weights, we can build a transition matrix, and this transition matrix is applied on the labels again and again and again until the algorithm converges at a point where the labels do not change too much. At that point, we can say that the labels have propagated from the labeled data to the unlabeled data, and we have a much larger training set, a training model from which we can build a more robust model. Now, one of the problems with this algorithm is that it's straightforward. It takes a straightforward Euclidean distance between nodes, but many times the vertices may not lie on a Euclidean distance. It may not lie on a straightforward, a planar graph like the one we saw just now. It can actually lie on a manifold structure, and there are lots of complicated mathematics by which manifolds are defined. We will not go into that because we will focus on a practitioner's perspective. From a practitioner's perspective, a manifold structure is one where data is distributed over low and high density regions. So it is not as planar as we saw in the label propagation case. There are clear high and low density areas. And what happens is here the geometry of the graph is not always described properly by Euclidean distances. So we might have to think of other distance measures. Such data is said to lie on a manifold. I'll show you a diagram of that, but I'll just quickly give you some of the key properties of the manifold. And it is also seen that the high dimensional data, for example, images are obviously high resolution images always lead to high dimensional data, or even a text data like web page classification, that those are high dimensional data. So high dimensional data typically leads to manifold structures more often. This is not necessary, but this is what we see very often. And then there's a further level of complexity. Sometimes there could be more than one manifold somewhat intertwined in a structure, in a data distribution, and then we call it a multi-manifold. So let's see how they look like. So this is a single manifold structure. There are two examples of single manifold structures in this diagram. One is called a Swiss roll. If you look at that diagram, there are lots of points. Now here the blue points belong to one label, let's say 0, and the green points belong to another label, let's say 1. But remember, we are dealing with semi-supervised learning, so not all of them are clearly labeled at the beginning. The labels come gradually as we run the algorithm. So what happens is, if you look at the figure carefully, there may be some data which is unlabeled and which may appear to be close to a green point. Let's say some point here is actually unlabeled, so we don't know whether it's a blue or a green. Let's say it's white. Okay, so this point can be misclassified as a green point. whereas it is blue. This happens because of the underlying manifold structure. If it was not a manifold, if it was a planar structure, this would not have happened. So these Euclidean distances could be very deceptive. Similarly, the two-moon structure, these are actually synthetic data sets. We'll also look at some real data sets, but let's look at a synthetic data set just to get the idea right. So this two-moons data set, you can see there are these orange points and these blue points. So let's look at this orange point somewhere here where I'm pointing my mouse. So let's say it is not labeled already. So this point is very close to the blue point actually. This point is very close to the blue point compared to say another point over here, another orange point. So let's say all these points are unlabeled, okay? All these points are unlabeled and these points are somewhat labeled orange. So any point over here would appear to be closer to a blue dot rather than an orange dot. What it means is that if there's a chance that it could be misclassified unless we use a proper algorithm. So the label propagation algorithm, the simple label propagation algorithm may not work in such cases. Obviously, we don't know whether data is on a manifold or not. How do we do? So we probably first run a label propagation algorithm. It doesn't give a good result. Then we guess that maybe the data falls on a manifold structure, and then we try a manifold algorithm, and so on and so forth, like we do in any machine learning project. But because we cannot always visualize points like we did over here, it's not possible to visualize. We can only try out different algorithms and see which one gives the best model. Now this is a multi-manifold structure. See, this is a dollar symbol. This is also it's actually a multi-manifold structure because this is one manifold. The S is one manifold, and the line in between, that is another manifold. This can also, it's possible that some data is very complicated and it falls on a multi-manifold distribution. Similarly, the one on the right is called a surface sphere. All it means is that you have a plane and you have a sphere which is actually cut through by that plane. So these are good synthetic data sets based on which some of these algorithms have been perfected. But once they've been perfected on the synthetic data like the dollar symbol or the surface sphere, they work and produce good robust models on real life data too. Okay, so if at all my data is distributed in that fashion and a planar graph does not work well, then what are our options? So this has been an area of research over the last 10-15 years, and a few interesting algorithms have emerged. So I'm going to quickly highlight 2 or 3 of those algorithms at a high level and explain why they work, because it's very mathematically intensive. We as practitioners probably need to understand the key reasons how those algorithms work and then be able to apply them to our projects. So one algorithm is called manifold regularization. This is actually for a single manifold, and what it does is it tries not just to find the distances mechanically, but it tries to find similar connectivity between similar nodes by staying along a high density region. Let me go back to that figure. See, if I want to classify some point over here, one way of doing it is mechanically finding the distance between some of these blue points and these points. But if I do that, I'm actually crossing over a low density region. There's no data over here. So this is called a low density region. So the manifold algorithm that I'm talking about imposes another condition that we not only need to find the connectivity between similar points, but connectivity through a high density region. So that intuitively would lead us to a path something like this or a path like this on a high density region. So then we have a better chance of classifying those data points accurately. How is it done? Mathematically, it involves a lot of mathematical theories, which we probably don't have to go into all the time, but it's good to know that it creates a weight matrix, weight between the edges. Now, this does not have to be a fully connected graph. Typically, what is done is you take k nearest neighbor graphs. So you create a graph out of k nearest neighbors for every point, every data point, because otherwise, if you have a very large number of data points, this matrix can just become very large. And then it derives from that weight matrix certain matrix called L, which is actually called a Laplacian matrix. These are just some jargons, but what is important is that it computes the top n eigenvalues of L. What those top n eigenvalues does is it constrains the problem to the high density regions, the regions of the highest density. And then there's the indicator function, which takes a data point and multiplies it by, it takes actually a dot product of those eigenvalues and this data point. And then depending on whether the output is greater than 0 or less than 0, we can classify it into one or the other class. So this is how the data pipeline will look if we run this algorithm, and this at a very high level. We have the weight matrix, which we can easily compute from distances. We are still working on the Euclidean distances, but remember, in the next step, we have immediately switched to the Laplacian matrix and no longer working with the vanilla weight matrix. And then we have an eigen function, the eigenvalue computations. Now we have a data point x. A data point x with a dot product with an eigenvalue will produce an indicator value. If it's greater than 0, then it's one class level. If it's less than 0, then it is another class level. So that is how this algorithm works. And we'll come to some implementation of this as well in a later slide. So this is about a single manifold. What about multi-manifolds? In case of multi-manifolds, the algorithms emerged a little later, and the mathematics appear to be a lot more involved. The algorithm itself is actually a lot more lengthy algorithm. We'll see. So here, this algorithm actually switches to a different metric of distances straight away. It actually creates a certain distance called Hellinger distances, and it creates the k nearest neighbor graph based on those Hellinger distances. And then it creates a spectral clustering. What is a spectral clustering? We all know k-means clustering. So basically, we have k centroids and we have data floating around those centroids. This works if the data is nicely spherically distributed. But if the data is like the 2 moons data that we saw here, then the proper algorithm to use for clustering is actually a spectral clustering algorithm. So that spectral clustering algorithm is embedded in the multi-manifold regularization, and that leads to exploration or discovery, I would say, of the high density regions separated from the low density regions. And this is how the algorithm looks like. It actually creates a sample covariance matrix, then it creates a k nearest neighbor graph, it does a spectral clustering, and within each cluster, it creates self-trained models of the data, based on which it can then identify any novel data based on which cluster it falls into. So this is again a lot of underlying mathematics, but fortunately, if we abstract it out, it can be programmed, it can be nicely implemented for actual machine learning projects. Now we'll talk about one more case of manifold structures. So nowadays we come across a lot of data that can be easily I'd say resolved into two or more views. So a quick example of this is web page classification. A good web page classification may depend not only on the bag of words, but also on other features of the web pages. For example, links to other web pages, because that is also a rich information that you can exploit. Okay, so this sort of data is called multi-view data, and this is somewhat related to multimodal data as well. Though typically multimodal means for the media data like video and audio or text and speech and things like that. But to a large extent, there's a lot of similarity. So we talk about multi-view learning. So there's yet another algorithm which actually applies to multi-view algorithm, multi-view data distributed on a manifold structure. So we have talked about single view data on a single manifold. We have talked about single view data on a multi-manifold, and now we are talking about a multi-view data on a single manifold. So this can also happen because of the importance of multi-view algorithms, multi-view data. This has also been researched to a certain extent, and we have an algorithm called coregularization. It actually boils down to a convex optimization. All we are trying to say here is that yes, it is also, this problem is also lends itself to a feasible solution. So how do we implement these algorithms because as practitioners, our intention could be more towards applying these in projects rather than having to dig into the rather detailed mathematics of it. So here we have actually come up with little implementation of some of these algorithms, and we plan to add some more. That is our contribution to this field more as practitioners. So you can find it on GitHub. The link is there right now, and it's based on Python 3.x. So a lot of people use Python for machine learning. So our implementation follows the scikit-learn patterns very closely. So you'll find exactly the fit method, you'll find exactly the transform method, you find exactly the parameters method, the config method, and things like that. You'll probably use the fit method more often, and the fit method will take a couple of fit method will take actually it will take 3 parameters instead of 2, because we are talking of semi-supervised learning. So it will take the data point, the attributes known as X, it will take the labels known as Y, and it will take attributes of the unlabeled data. We will call it XL, YL, and XView, which means the attributes of the labeled data, the labels themselves, and the attributes of the unlabeled data. So if you look at some of these algorithms, which I'll leave it to you to go through this at your spare time, you'll find the interface very similar to scikit-learn. So it just with a little bit of linear algebra and the common NumPy routines, we were able to implement some of these algorithms, and we have also created a synthetic data set for you to exploit. So you have some of those synthetic data sets which you can generate, and you also have a way to generate the MNIST handwritten digits data. So hopefully, with a little background, an overview of the mathematics of these algorithms, you can possibly try and use the implementation in some of the projects where it makes sense, and possibly even participate in the project if you want. So interestingly, scikit-learn today only has a label propagation algorithm. It does not have the manifold algorithms. So this is something which possibly this particular project on GitHub, this can possibly narrow that gap, and we can all participate to make it even better. So this is an early access release, but we plan to publish a few more algorithms and run a lot more experiments with these algorithms. So to close this session, we just want to summarize. Manifold regularization is an improvement on the standard label propagation algorithm, which is the baseline graph-based algorithm for semi-supervised learning. So we have the graph-based algorithms, we have the non-graph-based algorithms for semi-supervised learning, and we have graph-based algorithms which typically outperform the non-graph-based algorithms. Among the graph-based algorithms, manifold regularization is something that can address a lot of data sets which are hard to address with a planar label propagation algorithm. And it actually covers a wide range of scenarios, not just the Multiview data sets. Actually, there's an algorithm by Goldberg again, which is for online mode. So you can actually do classification on online data, on a data stream, instead of batch mode data. So you can probably look at some of those algorithms as well. And here are the references. Notably, you can find that most of these are 10, 15 years fairly recent compared to the classical, statistical machine learning algorithms, which is there in scikit-learn as well as neural networks. So this is an emerging field. A lot of things have happened over the last 10 to 15 years, and possibly we'll see more research as well as implementations on this area. So thanks again for listening, and hopefully I can come back later for taking a few questions.
Thank you very much, Monojit. That was really, really interesting. I learned a lot there. I completely forgot about manifold structures, so that was really, really interesting to see the explanation around that and talking about different implementations for how you might go around discovering those. So we'll have a bunch of questions on that at the end. So what I would like to do now is to move on to our next talk, which is with Aleksandra Asanin and Reuben Teijeiro from the UPAL group. So I will hand over to you both now. Sorry about that, everybody. I was on mute. I do apologise. Thank you very much for that, Monojit. That was really, really interesting. I learned a lot there, and I'm looking forward to some of the questions we have around that and to learn a bit more about use cases for that. So we are now going to move on to our next talk. So that is going to be with Aleksandra Asanin and Reuben Teijeiro from the UPAL group. So over to you both now.
Cool. Okay, I hope that you can hear me now. Oh yeah, yes. Okay, so I hope that you can hear me now, right? It's good to go. Okay, perfect. So let's get started. Welcome everyone to our Notes 2020 extended session. We're going to talk about how Neo4j helped us, at least in the recruiting process, or during the recruiting process. I'm going to do a quick introduction about Aleksandra. She's my colleague. She works as a data scientist. She's really passionate about discovering new technologies in the area of the digital transformation, and she is always eager to experiment with new technologies. And she's a really good professional, also certified in Neo4j, and yeah, she's doing wonderful work for together with us at the Jupyter group. I'm Reuben. I'm co-founder of Jupyter. We started the company 4 or 5 years ago. It's made in Sweden, even though I'm from Spain. But yeah, we have been working for large organizations, for so long. I personally, I'm an open source advocate, and with since I started, when I was a child with my first computer. So I really love technology. I really love open source, you know, the philosophy behind it. Yeah. So about Jupyter a little bit. Jupyter, as I said, was born in Sweden, and now today we have presence in a lot of countries. I don't know if there are like 8 or 9 countries, but at least I can mention a few of them, like Netherlands, UK, Spain, Hungary, Ukraine, Russia, Guinea, and Dubai at the moment. And we operate worldwide. We're a fully remote and distributed company, meaning that all people are located in different places. I don't really know where people is working, but at least, you know, they are like providing good value, and they're as long as they are happy, you know, wherever they are working, that's the best benefit for our organization, right? So regarding the problems that we are addressing, and the reason that we wanted to, you know, to do this talk is this year it has been a little bit chaotic, I guess, for everyone. And as you may know, you know, there were a lot of people lay off, you know, in different companies, large companies like Mozilla. Like sadly, they had to, you know, let people go because, you know, the crisis, you know. So yeah, we noticed that they were the market was changing. There was a lot of, you know, demands coming, you know, and that overflowed or recruiting process. So we just tried to scale up, you know, with human power, but that was not enough. You know, you know, you really need to do something. And you know, as usual, we take technology and then we try to make technology, you know, help us in this situation. So we investigated how, you know, we can work in the you know, in mitigating, you know, this issue and address it, and you know, and also at the same time try to offer a different way of work, you know, for maybe you know about the gig economy and the, you know, and this new way of not working full-time in something, but just working part-time in different things for different customers, different projects. So for that, we decided to create something that should be platform-driven. That's where we started with the ideation. So it should be a platform-driven, meaning that you know, people really like to, you know, to have a place where they have all the information. Maybe you can just find a new job directly from your smartphone while you are commuting or while you are having a dinner, you know. So also people really like to work with a flexible time, and also flexible locations. That also includes that we can offer better rates, and also distribution for location is really beneficial for a company. Having people distributed along different time zones is really beneficial, and mostly when you have, let's say, customers around the globe, as well in different time zones, or even support, you know, teams or help desk teams, you know, to provide this kind of support for people in different locations. So more or less, this is what we ideated. And the gig economy, as I mentioned, what it essentially is like a flexibility, meaning you really want to work in what you like, and you be able to change whenever you want. So that's one of the things, including freedom, freedom of choice, freedom of also learning. A lot of people really want to work in something because they are going to work in a project where they are going to develop new skills, test a new technology, or even work with people that they are mentors for them, right? Also, the gig economy allows anyone to get some additional income apart, you know, or aside of the regular work. You can just get a small gigs, during your spare time to just generate a little bit more of income. And if this kind of ad hoc, jobs, they're starting to populate more and more. Also diversity, bringing this kind of opportunities for, let's say, anyone, that allows to have a completely diverse team in your organization. This is something that we at the Jupyter Group are really proud of. We have a really diverse team from different countries and from different backgrounds, and that's one of the things that makes our experience working together better. And also, better opportunities and a career balance. So meaning that you not only are working in new stuff, but you are also, drawing your career path. You decide where you want to go, So after all of this, we realize that we are generating like a large amount of data, and this is where Aleksandra jumps in.
Yeah, so as Reuben tried to explain, we really believe in gig economy strategy, and we fully encourage that nature of work, because lifetime employments are becoming a history, and are already a history in some fields, especially IT industry. So people who participate in gig economy are from variety of backgrounds. Some of them are part-timers that work for additional income besides their full-time job, or some people are fully devoted to earning for life based on on-demand jobs. And millennials tend to change their career paths very often, so gig economy is a perfect infrastructure to support such a trend. These people see gig platforms as an alternative to generate incomes in more flexible and dynamic manner, and it allows them to have their own schedules, pick up only projects that they like, and they can work from anywhere, which is, of course, in COVID times very essential. So data that we capture about candidates, about people, is really important in order to make better redistribution of people in such a fast-moving pipeline where people change jobs very often and look for opportunities that match their needs better. And so here we have data about experience, previous work experience of people, their education, technical tests that they have passed, allocation, certificates. All this comes into play when you have different positions where it's important what languages do you speak, what skill set do you hold. It might be important also what degree you hold, and many other aspects, not to mention personality, how do you fit in teams, and so on. So what can be relevant for hire? Of course, apart from skill set, that they're basic thing, your fields of expertise, where are you based, are you able to relocate or not, do you have visas for specific country, also, what is your availability? Are you available for 6 months or 1 month? Everything comes into play when deciding which candidate to allocate to a specific position. So here we've come, sorry. We come up with some data model that is taking into account all these things, starting from a candidate and a relationship of candidate and country, where a candidate can have visa for country, live in country, but born in a different one, or just works in a specific country. Candidate can speak different languages, can hold certificates in different skills, can also have different skills or role. Maybe in past these people worked in some different roles, now they work in new ones. They can hold a specific degree, and so on. So how the workflow goes is that candidate usually comes from a recruiter or is associated with a subcontractor, because usually we also work with subcontractors. And when this candidate applies for position, it's evaluated whether skills that are required for a position are matching the skills the candidate has. And based on the percentage of match, the algorithm goes through all the candidate and provides the ones that are the best match, of course, for the job. There we also capture relationships between what candidates are assigned to what projects, so that in some later point of time we can evaluate, okay, who are the candidates who already worked for this client, what is the client feedback for these people, are they willing to hire them again, were those people a good fit for their teams, and so on. So basically, this is a basic model where we are considering relationships as a first-class citizens, because without relationships we wouldn't be able to capture different insights from data that would otherwise be very time-consuming to do through a relational database, going through rows and columns and doing a lot of joins to achieve the same thing. This is the usual data that companies hold about their employees. It's most commonly HR people have a clue about their employees based on their resumes, which of course in a lot of situations are not updated recently, contain legacy data, and are not really relevant for deciding whether a person is a good match for position or no. So if we take into account social aspects of social activities of people, if we take into account the communities they are active in, where are they contributing, are they volunteering in some organizations that are somehow connected to positions they are applying to, are these people writing blog posts on Medium, or have their own blogs? Do these people visit conferences? What people do they meet on those conferences? Does these people ever worked in the same environments? And also, who are the inspirations, people who inspire them, and who are they following on social networks? What topics are addressed by those people they are following? All this can bring a lot of value in crafting a personality and whether they're going to be a good fit for some position in some company or not. Why modeling all this into a graph? Well, capturing all this is essential for understanding aspirations, goals, aims, competencies of people. It happens a lot of time that organizations start looking for new resources before they even evaluate what people that they already have in organization really know, and whether their potential is fully utilized or not. This results in maybe internal feeling of people that they don't have enough opportunities for career advancement, or their potential is not utilized enough, and so on. Of course, many dependencies between data are not obvious at the first glance before you deep dive into the graph query, second and third layers, where you can maybe figure out who are the people with similar interests or learning similar technologies or taking similar career paths, so that you can group them together in teams and extract even bigger value from their collaboration. Of course, querying is faster and more intuitive. Just chaining the relationships that you are interested in is very easy in Cypher, comparing to long SQL joins and queries that you would have to write otherwise. And in the end, of course, people naturally fit into a graph data model and the networks itself, because graphs capture data as it naturally occurs in life. And it's very easy and intuitive to model this into a graph where you can later apply different graph algorithms and machine learning algorithms to detect communities, teams, clusters, and other stuff. Yeah, I even have a slide that refers to this. You can, with pathfinding algorithms, you can even detect career paths that people are taking. You can maybe do a different recommendations for their new trainings that employees can take in order to be successful in their direction that they decided to take in their career. You can recommend learning new skills that would be a perfect fit for their career path, and you can do you can get other similar insights into your people and organization and how it works. Yes, since the platform that we are internally building is in Drupal, Reuben can say a little bit about that because he's has experience in Drupal for 10 years.
So one of the reasons, I mean, we have been using Drupal for more, I mean, since the beginning of the when we started the company. I've been an active contributor of the Drupal community for more than 10 years. So most of our platforms are built using Drupal, and why not connecting Drupal with Neo4j? So there was already a module for, that connects or exposes Neo4j to Drupal, so we can just sync entities from Drupal directly through Neo4j and represent them as nodes. And yeah, the thing is, we launched a new version of Drupal. It was Drupal 9, and the module was not ready. So we took it, and then we working upgrading the module, fixing some bugs and so on, and giving it back to the community. So this is the way we work. We love open source. So a part of Neo4j, we also love Drupal and other open source projects. And this is the way we operate at Drupal. And yeah, at the moment, what we are doing is our web application where the users are interacting. What it's doing is replicating the data after normalizing it and cleaning it up a little bit, replicating in Neo4j, building the graph, adding more context to the graph. So whenever there is a query or any search or anything in Drupal, we can always trigger the query into Neo4j and get the results immediately. As Aleksandra mentioned, querying Neo4j is much faster than querying an MySQL database. So for us, it was a really, really good improvement, switching part of our job, into Neo4j. We're really satisfied with that. And not only that, I mean, we are not just, we don't stop here. So so for at the moment we are also using Neo4j in other areas in Drupal, not only in the recruitment, but for example we have also our own private cloud system. It's a hybrid cloud that we develop ourselves using open source as well, and what we are doing with Neo4j is representing our cloud infrastructure in the graph, meaning that we know how many data centers we have, how many servers are in each data center, how many services, applications, users. I mean, from knowing, you know, in a second, knowing who has access to what, and what kind of firewall rules are there. You know, this is exactly the data that we are representing in the graph in Neo4j for our cloud infrastructure. Regarding healthcare, the other co-founder of Drupal has a company in Sweden that is related to doctors and nurses. And yeah, doctors and nurses in Sweden, and they are like IT consultants. You know, you hire them for 1 week, 2 weeks. You know, they can relocate and so on. So it's exactly the same model. So why not reusing everything that we have in the recruitment process and put it back there? You know, just instead recruiting IT consultants, we can do it for doctors and nurses. So it's actually working really fine. So we didn't have to do a lot of more, you know, customization or personalization. So we reuse almost 80–90% of what we had already. And in education, we are also partnering up with U-School. That is a Swedish company where they are doing online courses, you know, or online education. And given the current situation with COVID, this is something that we didn't expect, but it came to us. And yeah, and there is a lot of demand in e-learning. Like you know, there is a lot of, you know, schools where the teachers are not prepared, they are not savvy in doing e-learning because of, you know, technical complexity or because of some lack of experience. So we saw this increasing, you know, the demand and so on. So the thing is, we are now adapting, you know, this e-learning platform into a Neo4j graph. So extracting the data that we need and what kind of, you know, context we want to give to the data, adding more metadata and so on. So at the moment, this is in a design and ideation phase, but I guess we will be able to also, you know, to reuse a lot of components and put Neo4j back to work into this platform as well. Exactly.
Yeah, I think this would be all from our side. I hope it was interesting. Let's see if we have any questions.
Yeah, thank you very much.
Thanks.
Thank you very much for that. It's very, very interesting. Again, it's really interesting to see how the thinking is coming around recruitment and skills matching and getting the right people to skills and roles and that kind of thing. Okay, so let's do some questions.
That was cool. Yes, thank you very much. Questions. Yeah, I had noted one down for Monojit. Maybe start with that. Kat wanted to know, is there a difference between single and multiple manifolds, that multiple manifolds intersect themselves? If you know what she means, or should she maybe explain further?
Yeah, that is correct. Multiple manifolds may intersect themselves. The data may be distributed in a way that, so just look at, for example, the dollar symbol. So there's a single plane that can intersect the S. Of course, that is a synthetic data set, but in real life also this kind of intersections can come into picture, and the algorithms. That is where the algorithms have to look at not only the intersection point but also the data density. Basically, it looks at the connectivity through a high density region, so it can separate between a high density region and a low density region, and hopefully even with the intersection, it can potentially do a good job of classification.
Okay, cool, thanks. I mean, I must admit, I heard for the first time today what a manifold is. So it was cool. I think it's very interesting, and I got to learn that, you know, when 2 points are close to each other, they don't necessarily mean that they are belonging to the same cluster. So I think that is that's very interesting.
Excellent. So we also had a question from Clooney, which was concerning skills. How do you achieve the skills that are recognised the same even if inserted differently into the database? So an example, good example here, is C# and .NET. So how do you handle similarity of skills? So
Yeah, I can give a short answer, and then Aleksandra can correct me if I'm wrong. So, but at the moment, you know, yeah, we fought like a lot with this kind of situation. You know, C#, .NET, ASP. You know, I don't know. These are really correlated, but we have even more problems with Golang, or you know, Angular, for example. That we have Angular JS. You know, and even with the versions, right? So we gave it a try. We created a matrix of skills with weights. I don't know. We tried to rethink this over and over, and then we ended up in trying to get the context. I mean, we really want to know what the experience of this person. I mean, and sometimes not just knowing the skill. You know, like for example, this person knows .NET. Just .NET is not giving me the context. So what we try to do is like saying, okay, this person is a front-end developer. What kind of technologies are included in front-end? These ones. Okay, we see this person matches at least these technologies, and more or less we create a label or a stamp for this person to say, okay, this person is an .NET front-end developer or a Java backend developer. You know, this is more or less what we did, and Aleksandra can correct me now.
Of course, no one said that our algorithm is perfect, but we are improving it all the time, tackling from different angles problems that appear there in order to try to match a person with a job the more in the most efficient way, let's say. Regarding skills, we are trying to group them together, skills that represent the same thing, so that we don't have a problem if one skill can have different names or refers to the same thing. So that's how we basically do it, yes.
Yeah, and we can't stop you know, or avoid people just putting whatever they want in their resumes, right? So we had a few you know, experiences where people have really weird you know, skills or experience, so the algorithm doesn't get any points. So for example, people with you know, barman, or you know, or I don't know, side jobs that they have in their CV. So the algorithm, you know, gets crazy sometimes, you know. So these edge cases, we are also mitigating them, as I said, adding more context.
More data, we are learning
yeah,
more and more.
I think that's super cool.
Yeah.
Brilliant. No, it's really interesting.
Yeah, sorry, I didn't want to interrupt you.
No problem.
Not at all. I hope that the sound is better. I can see people say that there is some echo coming from the mic.
Yeah, I'm trying to turn audio devices off and on, so I do apologise if I'm cutting a couple of words off to mitigate. So a question for you, Monojit, with regards to the manifold structures. So you talked a lot about different ways you can normalise them and some of the different approaches. And something that struck me in my mind was, can you think of some use cases or examples where you've already got the graph-based data? So I know you talked about how images are obviously images can have multi-dimensional, and even the idea of certain signs, so a euro sign or a dollar sign, it's not going to, you don't have this obvious, as you're saying, Euclidean distance points to pull out your clustering. Can you think of any graph sort of connected examples where this kind of thing might be useful to pull out, to use these approaches to cluster your data if it's in a graph-like structure?
Yeah, sure. So firstly, I would look at it this way, that any problem where you feel semi-supervised algorithms are a better fit than supervised algorithms. That is your first that is the first first approach, because you want directly go into the use cases may not be for the manifold algorithm per se, but it would be for semi-supervised learning. Now, once you decide that you want to use semi-supervised learning for a particular use case, and that further there are many use cases. As I said, that there are many cases where the data is scarce, the labeled data is scarce, but a very small label data set may not help you build a robust model. So that is where you want to get some of the unlabeled data as well, to get a proper picture of the data distribution. So text classification is a very good example. The way, say, New York Times, how do they tag their data? It's not possible for those millions of web pages to be tagged by humans. So obviously, they may have a small section which is already tagged by humans. Based on that, they can tag many other web pages, so that when we read these news items, whenever we read a particular news items, we see similar news items somewhere on the web page popping up and helping us get more relevant information and connected information. So that is a kind of even in healthcare, for example, you won't have a lot of X-ray images tagged as diseased or not diseased, normal. So there is also a lot of scarce data. So there is where you bring in the semi-supervised algorithms into play. Now, having decided to use a semi-supervised algorithm, you're not sure immediately whether the data is lying on a manifold or not, because you cannot visualize a large dimensional data like we have done in our presentation. That was easy. We just took some synthetic data, but that's not possible for real life data. You cannot easily visualize something that is more than three-dimensional. So the way we start with the simple algorithms, and then we move to the more complicated algorithms. And the simpler algorithms don't give us a good robust model. That's also in machine learning, we often call it Occam's razor. So if you find a label propagation algorithm not building a robust model, that is where it might strike you that the data distribution that is captured by label propagation is not accurate enough. Can I look at some other data, other ways of capturing the data distribution? For example, my manifold algorithms.
Cool, that makes sense. And I guess I've got one more question for you, Aleksandra and Reuben, which will be, so you talked a lot about the advantages of using a graph database for this kind of data, and one thing you mentioned was the dependencies, and you potentially lose the dependencies and the graph brings that out. So do you have either something that's regularly happened or an anecdotal story? Is there an example where you've spotted an interesting discovery as you've been putting this in as a result of having it in there?
Dependencies I was thinking about, you can discover how different career paths people can take and end up in the same career point, for example, or how different skills are related to the same role, or those kind of patterns that otherwise you wouldn't be able to spot if data was placed in rows and columns.
So, I mean, thanks to the graph, we can visualize communities. And that's one of the things that help us, to understand, in which areas we are having like enough, let's say, candidates in our database, and in which other areas we are lacking. And we also are adding context from the market, meaning that we know the demand as well. And then we match with the people that we have in the database, meaning that we understand, okay, now we know that PHP is starting to be trendy again in 2020. And then we know, oh, how many PHP developers do we have? Okay, we have just a few. Oh, we need to improve this. Okay, so this is the thing that we want to automate, meaning that this is going to be like an automated process. The system is going to be smart per se, and we are using also marketing automation, including in the whole ecosystem, meaning that we can automate campaigns for specific technologies, for recruiting or hiring people in this specific field.
Cool, thank you very much. Okay, so I think we are running a fair bit late, so thank you very much everybody for joining us. Thank you to our wonderful guests for those brilliant presentations. Learned a lot. They're really exciting to see.
Absolutely, yeah.
How we can apply this stuff. Absolutely, and the updates as well. And the people are using stuff. So we're going to leave it there. Thank you very much to all our guests once again. Thank you to everybody viewing as well. And our last Note extended session is next week. So we've got the details of that we'll put on shortly. So apart from that, thank you very much to our panelists. Thank you very much for joining us. Have a wonderful day and see you next week.
Thank you all. See you next time. Bye-bye.
Bye.